Hello and welcome back to Unacademy. So let's crack NEET PG. Myself, Dr. Muskan Chaudhary, and I will be guiding you through NEET PG on a microbiology subject. So today we'll cover a small topic that is a microscope. As we know, Unacademy is the India's largest learning platform with the daily live class in which the educator and the aspirants can engage in discussion, can ask their doubts, and can do the answer polling that to all within the live class, right? Live test and quizzes, that is to evaluate your preparation with the regular mock test and the quizzes and get detailed analysis of our performances, but with unlimited access to all our live classes. And those students who are the periphery are not able to get the live sessions, they can actually watch the recorded session. Now, one of the biggest perk is that of the PrepLadder and the Unacademy has collaborated together to give the best of the Unacademy for the live class of the batches, and to get the video lectures of all the subjects and the printed notes and rapid revision course for the and the video discussion of all the previous year's courses. Right now, 3 year of professional examination was given with a doubt clarification with raise a hand features, that is something new to the Unacademy and to the platform. And FMG batches, that is you can get the PDF notes for the session, integrated approach for all the topics that are being covered, and recorded sessions are being provided. Now, with the 12-month subscriptions, you also get 2 months free. So I recommend you to have at least one e-subscriptions that will cost you around 40,500 after 10% of the discount, right? And I will recommend you to have at least 1 to 2 subscriptions, because for the most of the competitive exams, at least 2 subscriptions, that is one e-subscription, something that is needed, and I will recommend you to have it at least one e-subscriptions, right? So if you find in the error in the slides of the educator, you can let us know and win the exciting offers and the prizes. Now, moving to the today's topic. Today's topic is a small little one. That is the microscope. We'll read a little about the microscope. Okay, so coming to the microscope, the microorganisms are extremely small, and the size of the bacteria, fungi, and the parasites is expressed in micrometers. That is, whereas viruses are measured in the nanometers. Now, most of the bacteria of medical importance generally measures about 0.2 to 0.15 micrometer in the diameter and about 3 to 5 micrometer in length, right? Viruses, the majority of the human pathogenic viruses range about 20 to 300 nanometer, and the bacteria about zero point 0.2 to 1.5 micrometer. Coming to the parasites, they greatly vary in the size. Now, protozoans measures in micrometer, and helminths range about few millimeters to several meters. Now, fungi, most fungi grow as hyphae, which are cylindrical thread-like structures 2 to 10 micrometer in the diameter and end up to several centimeters in the length. Some fungi grow as yeast round to oval unicellular budding cells of 4 to m micrometer in the size. Some parasites such as adult form of the helminths are visible to the naked eye, whereas rest of the microorganisms, due to their small size, cannot be seen distinctly with the unaided eye but need a microscope for their visualization. Most bacteria, parasites, and fungi can be observed by the light microscope, whereas viruses need electron microscope. Therefore, for viruses, we use the electron microscope, right? And therefore it is understand important to understand the functioning. Now, microscope refers to the use of the specialized instrument that is called microscope to view objects and areas of objects that cannot be seen with the naked eye. There are various types of microscopes that are used in the diagnostic microbiology. That is, one is the bright field or light microscope. Next is the dark field or dark ground microscope. Next is the phase contrast microscope and fluorescence microscope and electron microscope. Okay. Now, moving to the properties of the microscope, a good microscope should have at least three properties. That it one is the good resolution, another it should have good contrast, and it has the good magnification. Right? So, properties of the microscope that it should have a good resolution. Now, resolution powers refers to the ability to produce the separate images of the closely placed objects so that they can be distinguished into two separate entities, right? So resolution is the power to produce the separate image of closely placed objects so that they can be distinguished two separate entities. The resolution of power of human eye is about 2.2 mm. Light microscope is zero point 0.2 micrometer and electron microscope is about zero point 0.5 nanometer. Now, resolution depends upon the refractive index and oil has a higher refractive index, hence oil enhances the resolution power of a microscope. Coming to the good contrast, this can further be improved. This can further be improved by staining the specimen. When the stain binds to the cells, the contrast increases. Right? Good magnification. This is achieved by the use of the lenses, and there are two types of lenses. That is the convex lens that is used. That is the ocular lens with the magnification power of the 10x. Objective lens that is a scanning lens of 4x. Low power and the high power. Low power we use 10x lens, high power we use 40x lens, magnification lens we use 10x, and the objective lens scanning lens of the 4x, right? And oil immersion lens that is the 100x. The total magnification is the product of the magnification of the objective lens and the ocular lens. Now next is the scanning field that we're using about the 40x, and the low power field that is the 100x, and the high power field that is the 400x, and immersion that is a field is added, that is into 10 we are doing. For the scanning we use 4x lens, and for the field we are using 4x. Low power using 10x, and the low power field we are using 100x. High power we are using 40x. For the high power field we are using the 400x. For the oil immersion we are using 100x, and for the oil immersion field we are using the 1000x, right? Now, the bright field or the light microscope. First, we'll talk about the bright field or the light microscope. They forms a dark image against a they forms the dark image against a brighter background, right? So the bright field from the name से क्या हो जाएगा कि वो dark image बनाएंगे, brighter तो background होगा और उसके सामने dark image बनाएंगे, hence call the name structure. The part of the bright field are divided into three groups. Now first is the base. It holds the various part of the microscope such as the light source, the fine and the coarse adjustment. So this is about what this is the bright field or the light microscope, having the base and the C-shaped arm that it holds the microscope and it connects the ocular lens to the objective lens, right? So first we are talking about the base, that this is the base, this is the base with the light source, right? And another we are talking about the base, that is the C-shaped arms, that is it holds the microscope, right? So we are talking about the base and the C-shaped arm that is holding the microscope, that is the C-shaped arms that is present on the base and it is holding the microscope and connect the ocular lens to the objective lens, right? So this is the objective lens and this is the ocular lens. So this is the C-shaped arm right? C-shaped arm present on the base, and it is holding the ocular lens and the objective lens. Mechanical stage, the arm bears a stage with stage clips to hold the slides and the stage control knobs to move the slides during viewing. It has an aperture at the center that permits slides to read the object from the bottom. Right, so we are talking about the mechanical stage. So this is the mechanical stage on which we keep the slides, and it has an aperture through which the beam of light passes. So हमने क्या देखा, एक तो बेस होता है, एक सी शेप्ड आर्म होता है जो ocular lens और objective lens को connect करेगा, and one is the stage that is holding the slides. Now coming to the magnifying parts, one is the ocular lens, that is the arm contains the eyepiece that bears the ocular lens of 10x magnification power. Now microscope has two eyepieces, that is they are binocular. So they are what? They are binocular microscope. Next is the objective lens. The arm also contains a revolving nose piece that bears the two or four objectives with lens of different magnifying power, that is the 4x, 10x, 40x and the 100x. So we'll talk about the objective lens, that is of 4x, 10, 4, 10, 40 and the 100x. So this is the ocular eyepiece, that is the a binocular eyepiece that is having magnifying power of the 10x, and objective lens, that is the 4, 10, 40 and 100. C-shaped arm is present connecting the ocular and the objective lens, and a stage is present that is holding the slides. Now coming to the illuminating part, one is the condenser, that is the coming to the illuminating part, that is the condenser we are using. Okay, that is here you can see the sub-stage condenser. This is the condenser. Now it is mounted beneath the stage which focuses a cone of light on the slide. Next is the iris diaphragm, that is the aperture diaphragm control, that is the iris diaphragm we are using, and it controls the light that passes through the condenser. One is the light source and fine and the coarse adjustment knobs, right? So these are fine and the coarse adjustment knob. These are knob like structures. These are fine and coarse adjustment knobs. This is the condenser, and one was the iris diaphragm to control the light, similar to that of the eye. So C-shaped arm है, stage है, base है, lenses है, coarse and five adjustment knob है, and the substage condenser and the iris diaphragm. Right, now coming on the working principle, the rays emitted from the light source passes through its diaphragm and falls on the specimen. The light rays passing through the specimen are gathered by the objective and the magnified lens. Image is formed. The image is further magnified by the ocular lens to produce the final virtual image. So light reaches the object on the stage. We saw on the stage, that is light is reaching on the stage, right? And the condenser, we saw the condenser was present that will focus the light towards the sample. The patch stops providing in the condenser lens blocks light around the central region. Of the light that enters the specimen mostly is transmitted while some is scattered through the sample, right? If you can see, this is a condenser and the condenser, this is a condenser and it is focusing the light on the stage, right? And virtual image is formed that is seen up by the objective lens that is having a magnifying power of 10. Now coming to the next microscope, that is the dark field microscope, that is a dark field microscope Principle of the dark field microscope is that the objective appears bright against a dark background, and this is made possible by the use of the special dark field condenser. The dark field condenser has central opaque area, right? The dark field condenser has what? Central opaque area that blocks the light from entering the objective lens, and has peripheral annular halo area which allows the light to pass through and focus on the specimen. So what we are doing, the dark field microscope, the object appears bright against the dark background because we are blocking the light through the condenser, and we are allowing the light to enter the objective lens and having to pass through and focus on the specimen obliquely. Only the light which is reflected by the specimen enters the objective lens, whereas the unreflected light doesn't enter the objective lens. As a result, the specimen is brightly illuminated, but the background appears dark. Right? Dark field microscope is used to identify the living unstained cells and thin bacteria like spirochetes, which cannot be bacteria visualized by the light microscope. So we are using it for the spirochetes because they are not visualized by the normal light microscope. So this is what the objective lens, right? And this is the direct illumination block. Only scattered light is transmitted on the sample, and it is taken by the that scattered light is taken by the sample, and therefore the light where it is focused, only that appears the bright against the dark background. Now next is the phase contrast microscope. As per its name, phase contrast microscope, the contrast enhances. Okay, the microscope visualize the unstained living cells by creating difference in contrast between the cells and the water. It converts the slight difference in refractive index and cell density into easily detectable variation. So what does it do? It converts the slight difference in the refractive index and the cell density into easily detectable variation in the light intensity. Contrast can also be enhanced by staining the specimen, but as staining kills the microbe, the properties of the living cells cannot be studied. So in the contrast microscope, the contrast is enhanced, that is the by converting a slight difference in the refractive index and the cell density. The condenser is similar to that of the dark field microscope, consists of an opaque central areas with a thin transparent ring which produces a hollow cone of light. As this cone of light passes through a cell, some light are bent to variation in density and the refractive index within the specimen, and are retarded by about one-fourth of the wavelength. The undeviated light rays strike a phase ring in the phase plate, while the deviated rays miss the ring and pass through the rest of the plate. The phase ring is constructed in such a way that the undeviated light passing through is advanced by one-fourth of the wavelength, and the deviated and undeviated waves will be about half of the wavelength. The principle is not that important. The background formed by the undivided light is bright, while the unstained object appears at the dark. The light rays goes through the condenser, and the specimen bacteria and the phase ring will form, and the it will be perceived by the ocular lens. Now application, it is mainly useful. The phase contrast is used to see the microbial motility, determine the shape of the cell and cell membrane, nuclei, intracellular components to see, which becomes clearly visible because they have refractive index markedly different from the that of the water. So on the basis of the refractive index and the cell density, we see what the motility and the shape of the cell and the intracellular components, right? This is the phase contrast, that is the bacteria. Now the rays are deviated by the specimen is 1/4 wavelength out of the phase. Deviated rays is half of the wavelength out of the phase, and deviated and undeviated rays cancel each other, and that is perceived by us. Now coming to the next, that is the fluorescent microscopy. That is the fluorescent microscope refers to any microscope that uses fluorescence property to generate an image. That is, we are using the fluorescence property to generate the image, and the principle is that fluorescent dyes are exposed to UV rays, they become excited and they are set to fluoresce, that is, they convert this invisible short wavelength into light of the longer wavelength. So what we do, that the dyes are exposed to what? They are exposed to UV rays. Okay, and the source of the light may be mercury lamp which emits rays that passes through the excitation filter. The excitation filter is so designed that it allows only short wavelength UV light to pass through, blocking all other wavelength rays. The exciting rays then get reflected by the dichromatic mirror in such a way that they fall on the specimen which is previously stained by the fluorescence dye. The fluorescence dye absorbs the exciting rays of the short wavelength, get activated in terms emit rays of higher wavelength. A barrier filter positioned after the objective lens removes any remaining UV light which could otherwise damage the viewer's eyes, or blue or the violet light which would reduce the image contrast. So what is important to remember is that they uses the fluorescent property to generate the image, and their fluorescent dyes are exposed to UV rays, they become excited and they convert into the invisible short wavelength rays into the longer wavelength rays and are perceived. Right now, application is that the epifluorescence microscope is just the simplest form of the fluorescence, which has the following applications, that is autofluorescence. Certain microbes actually fluorescence when placed, that is the cyclospora, and microbes coated with the fluorescent dye, that is they are stained known specifically by the fluorochrome dyes. Now, the principle we have already read, and principle, the questions on the principles are not as such asked, so you may skip this. Now, next is the acridine orange dye is used for what? The detection of what? Plasmodium and filarial nematodes by QBC. So, this is important to remember. Acridine orange dye is used for Plasmodium and filarial nematodes. Okay, that is QBC we are using. Next is the auramine phenol is used for the detection of the tubercular bacilli. So auramine we are using for the tubercle. Immunofluorescence, it uses fluorescent dye tagged immunoglobulin to detect cell surface antigen and antibodies. There are two types, direct and the indirect. Important to remember, acridine we are using for the plasmodium and the filarial, and the auramine we are using for the tubercle bacilli. Confocal microscope. It is an advanced design of the fluorescence microscope. It uses the point in illumination and a pinhole in an optically conjugate plane to eliminate out the out focus signal and to get a better resolution. Next is the electron microscope. So, electron microscope uses the accelerated electrons as a source of the illumination, because the wavelength of the electron can be up to 1 lakh times shorter than that of the visible light photons. The electron microscope has a much better resolving power than the light microscope. Hence, it can reveal the details of the flagella, fimbriae, and the intracellular structures. So, it is an advanced microscope and used to see what? To see the flagella, fimbriae, and the intracellular structures. Okay, it was invented E by E, that is the Ernst Ruska. Okay, so easy. Electron microscopes are further of two types. Now, one is the transmission electrons microscope, and another is the scanning electron microscope. Now, moving next to difference between the light microscope and electron microscope. Beam of light is of longer wavelength. For electron microscope, it is what? Of shorter wavelength, and it is large and not portable and expensive, while the light microscope is small and inexpensive, and not a lot of training is required because it's easy to manage. But for electron microscope, training is required, and images are what? A black and white, while in light microscope they are colored images. Now, the specimen for the electron microscope is dead, while it is alive and unharmed in the light microscope. And electron microscope is of greater resolution and of greater magnification, while it is of lower resolution and lower magnification for the light microscope. So this is the light microscope, and this is a stage, this is a condenser, and here's the iris diaphragm. This is the adjustment, fine and the coarse adjustment. This is the base. This is the C-shaped arm with the ocular lens and the objective lens. Okay? And this is the revolving nose piece to adjust the resolution, and the ocular lens of power 10x, while objective lens of 4, 10, 40, and the 100x. Right? So this was it. The class was short. This was it about the today's class. That important points were about the for the virus, the size is 20 to 30 nanometer, for bacteria 0.2 to 1.5 micrometer, and the fungi 2 to 10 micrometer, right? And the electron microscope that we are using, and to for fungi because they are very small in size, and the types of the microscope we show us. So properties are important: good resolution, good contrast, and magnification power we remembered. And in the bright field, the parts we saw, that is a C arm with this stage and the base and the objective ocular lens and the fine and the coarse adjustment knobs that were important with the body. And illuminated parts, we also condenser, iris diaphragm, fine and the coarse adjustment. The question on the principle is not that asked, you may skip it. Dark field, that is the background is dark against which the specimen is checked, right? Now for the spirochetes, we use the dark field microscope. And phase contrast, that is, the contrast is enhanced because of the refractive index and the cell density, and it is therefore used to see the motility and the shape and the intracellular components of the cell. Fluorescence, that is the fluorescence property we are using to generate the image. And there are various type applications we were seeing, that is autofluorescence we were seeing using for the cyclospora. Right now, acridine dye we are using for the plasmodium and the filarial nematodes, auramine for the tubercle bacilli, and right. And they are for the two types: direct indirect immunofluorescence, electron microscope, that is for isolated electrons are used, and transmission electron microscope and scanning electron microscope. Differences, we saw that electron microscope is more advanced, more expensive, training is required, resolution is greater, and greater magnification, right? So this was it for the today's session, and please do use my code, that is the Muskan, to get 10% of the discount on the NEET P subscription. I hope session was clear of today to short session, and I hope that everyone is safe at home and doing well. And best of luck for examination that is over the head. And do not panic, just have a good night's sleep. So a little bit of theory was covered in today's session. See you in the next class.